Black holes, arguably the universe's most enigmatic and intense phenomena, are astoundingly complex and bizarre. What occurs if one ventures inside? What would we see and experience if we were able to document the journey? First, we need to understand the concepts of space and time. Unlike a fixed stage, space is flexible, and time's progression varies across the universe, both being relative. Matter such as planets and stars influences space, creating a warped stage, which in turn influences the movement of matter. This is gravity, but black holes take this to an extreme. Think of them as cosmic trapdoors with mass so immense that they create areas where normal rules don't apply. So, let's imagine you are in space heading towards a black hole. You are staring directly at it. Or are you? Observing a black hole would actually look like, well, nothing. The space under their control is blocked by an invisible, one-way barrier called the event horizon. The event horizon forms a shell around a region of space that, once entered, is shielded from the rest of the universe forever. Because the black hole trapdoor deforms space so much, not even light can escape it. And with nothing escaping to transfer information from the inside, it's impossible to tell what it really looks like. However, the telltale signs of its presence would appear in the form of an accretion disk. This is a spiral of gas and other material falling into it. This material heats up due to friction and gravitational forces, emitting intense radiation, often in the X-ray spectrum. This glowing disk would be one of the most visible features as you approach the black hole. You would also see a mind-blowing example of gravitational lensing, which is light from other stars and cosmic objects bending around the black hole due to its intense gravitational field. This can create multiple images of the same object or distort the light in such a way that it forms a ring around the black hole, known as the Einstein Ring. Along with these visually stunning and strange views, you would begin to increasingly feel the effects of time dilation as well as increasing darkness and silence. To an outside observer, your movements would appear to slow down as you get closer to the event horizon. What would happen if you tried to get closer to a black hole or even enter it? This is where you need to buckle up, because it gets really freaky now. First of all, gravity is so strong near a black hole that, as well as matter, light will also orbit. If you were just outside the event horizon in what is called the photon sphere, you could look in any direction and you would see yourself as light from behind you travels around the black hole and into your eyes. Here, light from stars and other cosmic objects would be also severely bent, creating strange and fascinating visual effects. You might see multiple images of the same star, wildly distorted galactic panoramas, or even a glimpse of the universe in a full circle due to gravitational lensing. The immense gravity here would also alter the passage of time. The stronger the gravitational force, the slower time passes. So to anyone lucky enough to observe the one-way journey you are making, they would watch you in slow motion while you watch the universe speed up. If you have a change of heart and decide to fly away from the black hole, the effects of time dilation would mean hundreds, thousands of years or more would have passed for the rest of the universe. If you are brave enough to continue your journey into the black hole, however, an incredible and mind-boggling fate awaits you. Although it sounds innocent, spaghettification will occur where the gravitational pull at whichever part of your body is closest to the black hole would experience a much stronger pull than the rest of you. You would be stretched and compressed into, well, a strand of human spaghetti and gobbled up by the black hole forever. Spaghettification is only a risk with smaller black holes, since they have much smaller radii. If you go to the center of a galaxy and find a supermassive black hole, you might be able to experience crossing the event horizon. Strangely, however, that distant observer that would only see you moving ever slower would never see you actually enter the black hole. They would only see you slow down until you stop and then fade into non-existence. Meanwhile, from your perspective, assuming you survive being turned into a pasta dish, the void of the black hole rises up to envelope you until your only view of the universe you left is a tiny spot of light. As we journey on and cross the event horizon, we are now at a place from which we cannot escape. You are in a realm where the familiar concepts of direction and space as we understand them no longer apply. In this extraordinary environment, traditional orientations such as up, down, forward, and backward, lose their meaning. Any direction you move in would lead to the center. This is primarily due to the extreme curvature of spacetime, caused by the black hole's immense gravity. At the center of this bewildering region lies the singularity, an area where all the mass of the black hole is thought to be concentrated. The singularity represents a point of infinite density where our current laws of physics cannot adequately describe what happens. This is because the gravitational forces are so intense that they warp spacetime to an extreme degree, and our understanding of physics, which relies on spacetime being a smooth and continuous entity, breaks down. The singularity has no surface or size, so singularities might not even exist or be completely different things to what we predict. But this is all we know right now, from the best prediction we have, from our best current theory of spacetime. The mystery of what occurs beyond this point is one of the great unanswered questions in modern physics. There are several hypotheses and theories, but none have been conclusively proven. One such theory is the concept of a firewall at the event horizon. The firewall hypothesis suggests that there is a violent and energetic zone right at the event horizon. According to this theory, an observer falling into a black hole would encounter a region of extremely high energy, capable of incinerating anything that passes through. This idea emerged from attempts to resolve contradictions between quantum mechanics and general relativity, particularly around the concept of information paradox. The question of how information about the material that falls into a black hole can be preserved, as quantum mechanics suggests it must be. The firewall would essentially break down the material and its quantum information into a chaotic state, resolving the paradox, but at the cost of introducing new complexities into our understanding of black holes. It challenges the previously held notion that crossing the event horizon would be uneventful, a concept known as the no-hair theorem of black holes, which posits that black holes can be fully described by just three characteristics: mass, charge, and angular momentum. However, the firewall hypothesis is still a topic of significant debate among physicists. Some argue that it violates Albert Einstein's principle of equivalence, a cornerstone of general relativity, which states that free falling into a gravitational well should not entail experiencing any forces, i.e., it should feel like floating in empty space. In conclusion, it is important to understand a lot of what is discussed in this video is theoretical, because, well, we just don't know for sure. Some ideas are hypothesized based on our knowledge of related phenomena, and others, like the singularity, are mathematically modeled ideas that may not actually exist in a physical form. The best advice we can give is, stay away from black holes.